Morning. Yeah. Okay. I'm not Rajiv Allur. I'm Paritosh Pandya. It's indeed a great pleasure and honor for me to introduce today morning's invited speaker, Professor Rajiv Allur. Rajiv Allur is Zisman Professor of Computation and Information at University of Pennsylvania. He did his bachelor's degree in computer science from IIT Kanpur in 87 with, I believe, President's Gold Medal. And he went on to do his PhD at Stanford in 91. Now, this is the time at which he introduced his well-known timed automata model. Over years, that model has grown and become the standard automata theoretic model for understanding real-time computation. And Rajiv had a lot to do with pioneering the theory of timed automata and timed languages. He worked on diverse facets, timed automata, timed automata, weighted automata, even going beyond that, two-way automata, and logics of various forms. He's worked on things like computable decision procedures for message sequence charts, for nested word computation over nested words, and more recently on streaming string transducers. Recognizing his contributions to the field, he's been awarded the IEEE Logic in Computer Science Award for Test of Time Award. I guess must be to do with his theory has stood the test of time. I'm sure he'll stand test of time for many years to come. He's been awarded the inaugural CAV Award, and he's a fellow of IEEE as well as ACM. His research interests are, let me read you the official list and close. His research interests are, they include formal modeling and analysis of reactive systems, hybrid systems, model checking, software verification, logics and automata, and design automation for embedded software. So today he's going to talk about streaming string transducers. Professor Rajiv Allur.
Thank you. So that was a nice introduction. So I'm very glad to be here, and I want to thank Kamal and Meena for inviting me. So the last time I was at 98, and at that time also the meeting was here in Chennai, hosted by IMSC, so I'm glad to be back. So today I'm going to tell you about some work we have been doing on string transducers. But before that, let me give you some context for how I got interested in this problem. So I have been working on software verification for past many years. And the goal in software verification is to come up with a verification tool that would take as input a program and a requirement, a formal specification, and then try to check whether the program satisfies the requirement. And if yes, then come up with a proof, and if not, come up with some counterexample that would show the bug that the program doesn't meet the requirement. And increasingly, the action in computer science is shifting from performance to predictability and reliability, and the computer science discipline as a whole is getting more and more interested in this problem of how do we make sure that the software that's becoming more and more critical to the society's infrastructure is working correctly, working as intended. Now, anyone who has done a first course in theory of computation knows that the halting problem for Turing machines is undecidable. And finding bugs in program or verifying that a program meets its specification is just an instance of the halting problem, and this is an undecidable problem. But over the past decade, people have made dramatic progress on this problem. And here is an example of some program, and this is from a device driver. Here is C code, and what we want to check is that the the order in which this code acquires locks. So here is the instruction to acquire a lock, and here is an instruction to release the lock. And we want to make sure that every lock that's acquired is released, and it's an alternating sequence. Now that's a correctness specification, and recently people have been able to build tools which would take the C code as an input, or take this requirement specified in some formal manner as the specification, and then make sure that the code works correctly. And particularly for Microsoft, this problem has turned out to be very relevant in practice, where Microsoft tools can certify that the device driver code, which is written by third parties, actually meets the requirements, and that makes that's one of the things one has to make sure, that the operating system doesn't crash because a malfunctioning device driver. But more recently, people started looking at a code of this form. So the code that I showed earlier, and the requirement and the form of the code, everything was more related to control. So the order in which locks are acquired. Now this code is of very different form. So this is actually what's called a lock-free concurrent queue. So when you do the first course in programming, you learn how to write correct code for say doing insertions and deletions in a list, or writing code for NQ and DQ. And typically in a language like C, the way things are implemented is you have a sequence of cells or nodes where the cell holds data and the next pointer, and then this is how data is stored. And then to update the list, you have to start at the head and traverse the list and do some pointer manipulation operations to achieve insertion, deletion, or NQ or DQ. Now, when we go to concurrent setting, there would be multiple threads who would be accessing this list at the same time, trying to swing these pointers, and making sure that that concurrent code works correctly turns out to be quite challenging. And in fact, if you look at this textbook, which was published recently, I don't know if you can read it, it says The Art of Multiprocessor Programming. It's a book by Hurley and Shabit, which has instances of lots of concurrent data structures where the code looks like this. So one interesting thing about this code is that, so if you think about concurrent programming, so one standard way of implementing concurrent data structure is every time you want to access the queue, whether you want to NQ or DQ, you acquire a global lock. But that turns out to be quite inefficient when queues are used within the operating system. So this is actually a lock-free queue where there is no synchronization, there is no lock acquired. And in fact, the only synchronization appears in this call, which is a compare and swap instruction. So all modern multiprocessors support some version of compare and swap. So this is from the Intel's architecture. And so you have very low, so the synchronization is at a very fine-grained level. And so getting this code is correct is a big challenge. And in fact, there are bugs published in the published code, for example, the code that's in this book, or in Java's concurrency libraries, lots and lots of bugs. So the challenge for people doing verification is to develop tools that would take this code as input and automatically verify some properties. Now, it turns out that analyzing programs that manipulate this heap allocated data, it's a difficult problem. So for in the classical model checking, the underlying theory uses finite automata. So you basically abstract program as a finite state machines. If you have concurrency, you have communicating finite state machines, and a priori the space is bounded, and so most of the action is how to do the search efficiently. But for programs that manipulate this heap allocated data, there are no decidability results. So even even without concurrency, if you just have a list, and if you have a program with some pointer variables and that's manipulating this data, answering questions such as, can two pointers point to the same cell at the same time? So this is called aliasing. So can there be an aliasing problem somewhere? So such problems turn out to be undecidable. So the question that I'm interested in is how to develop algorithmic verification techniques for programs that manipulate heap allocated data. Right? So if you look at the if you remember that NQ example, we don't really need to know the details. But if you think about operations like delete, insert. So if you think about what's happening at the high level, so you could say the list is a sequence of data items, and insert basically inserts a data item into that list, right? So at the high level, the semantics of the function is a mapping from strings to strings, strings over data items to strings over data items. So that's basically what a transducer does. So why can't we use a theory of transducers or some decision procedures for transducers to get a more clean abstract versions of these problems? Just the same way as people have been doing using, say, push-down automata to analyze programs with recursion, or non-deterministic finite automata as an abstract model for programs with bounded data, or Buki automata to analyze programs which interact with the environment on an ongoing manner, and the requirements are about what happens over infinite time. Tree automata to analyze branching time properties of programs. And these techniques have actually been quite useful in gaining insights into which problems are decidable and how to formulate the problem. So our goal is to develop a theory of transducers which would be useful to analyze programs that manipulate heaps. So let me start by giving you some introduction to string transducers. So what's a transducer? So a transducer, in this setting, it maps a string over input alphabet to a string over output alphabet. So for pretty much most of the talk, assume that these alphabets are finite. At the end, I'll mention what happens when you have unbounded data. So the simplest transducer model is actually a finite state Mealy machine, where the transitions look like this. So if the transducer is in state Q, it reads an input symbol A, outputs 0, and goes to state Q prime. So this is just an extension of finite automatas. Typically, the DFAs, the deterministic finite automata that you learn in your theory of computation course, will have a state, a label, and another state. So here the only difference is there is an input and output. So one good thing about Mealy machines is that everything, if you think about analysis problems, problems like minimization, equivalence, it's pretty much the same as DFAs. But the model is not particularly very expressive. For example, if I want to, in our context at least, is if I want to say delete all A symbols, can't really do it, because when you read an A, you want to delete it. In a Mealy machine, you read an input symbol and produce an output symbol. Well, the problem, of course, the extension is kind of obvious. And these are called rational transducers. So what's a rational transducer? So you are in state Q, you read an input symbol A, and you output a string of output symbols. And this string could be empty, so the output string could be empty. So if I want to delete all A's, what I would do is every time I read an A, I output epsilon. If I read some symbol that's not A, I would output exactly the same symbol. Okay, so the transition function here is from states cross input to the new state and a string over output alphabet. So these kinds of transducers are called rational transducers. And you can do things like, well, delete all A symbols or duplicate each symbol. So here is a string ACB, AB, BC. If I want to duplicate each symbol, it's kind of obvious how to do it. Every time you read a symbol, you output 2 of those, right? So every time I read an A, I would output AA. So this string would be mapped to this. Or insert 0 after first B. So we want to model operations like insert and delete. So this seems a plausible model. And these are very well studied. And there's some nice properties. For the deterministic rational transducers, equivalence is decidable. So it turns out that these problems, the basic intuitions about automata hold, but require still a lot of work. In particular, what could happen is on 2 different paths, you may output exactly the same sequence of outputs. So the equivalence and things like minimization becomes a bit trickier. So it may happen that on an A, I output 0, and then I output 0, 0. On some other path, I output 0, 0 followed by 0. And so the analysis algorithms have to figure out that on different paths, even though locally you are outputting different symbols, concatenated globally, they turn out to be the same string. But you can do this analysis, and these have been used in various contexts. But in our context, like for program verification, they don't seem particularly, the expressiveness is not quite enough. So in particular, what about reverse? So reverse is one of the early examples that you do when you are learning about data structures. You can't really reverse because you have to read the whole input string and then output the reverse. Okay, so what about reverse? So there is a model called two-way transducers, and for our purpose, we just have to worry about deterministic two-way transducers. So what's a deterministic two-way transducer? So the input is stored on a tape, and there is one read head, and the machine is in some state Q. And when you read, the transition function tells you that if you are in state Q, if you are reading A, output some string, could be epsilon or could be 0, 0, and then the machine could say move right or could move left. It could say stop, I'm done producing the output. So these deterministic two-way transducers have some nice properties. In particular, you can compute things like reverse. So if I want to reverse, I would store the string on the input tape and then go all the way to the right and then just come back, and while on the reverse pass, just output every symbol. So kind of obvious how to do reverse. You can also copy the entire string. So for example, if my string is ACB, ABBC, suppose I want to output the same string followed by another copy of that string. So I want to map W to WW. It's kind of obvious how to do that. So you go start at the left, read the whole thing, at every step output what you read. Then when you reach the right end, come back. On the reverse pass, don't output anything, but then do another pass. So a two-way transducer can go back and forth on this tape. And you can also do things like regular look ahead. Suppose I want to do that, I want to delete A symbols, but whether I do that or not depends on some property of the string which I haven't seen yet. So in particular, suppose I want to say delete all A symbols if the string ends with B. So obviously a Mealy machine or a rational transducer can do that, because while reading the input, you don't know whether the string ends with B or not. A two-way transducer can easily do that. You can read the whole string, figure out if it ends with B or not, and then come back and then do the computation that's needed. So this class of transducers is called regular transducers. So the functions that you can implement using two-way transducers, that's known to be regular transductions. So everyone knows about regular languages. Not many people know about regular transductions, but it's a reasonably well-studied class. So in particular, there is a nice characterization of these regular transductions using what are called MSO-definable graph transductions. So I'm not going to actually tell you about this, the logic-based approach, because that's kind of, if you haven't seen it before, it would take a bit of time to explain how that works. But let's just take it for granted that for everything that I'm going to talk about, there is an equivalent logic-based characterization. Just the same way as there is logic-based characterization of regular languages. So that's an evidence that this class is robust. It has different characterizations. And in our context for verification, one nice property is that checking equivalence of two-way transducers is decidable. They are closed under operations such as sequential compositions. If I want to say f of w is f1 of f2 of w. So if f1 and f2 are regular, f is also regular. So just sequential composition of functions. But as far as I know, that there has been no application of two-way transducers, at least in the context of program verification. And one plausible reason is that this is not how programs work. So if the program that you would write to reverse a list has almost nothing to do with the way a two-way transducer does reverse. So two-way transducers could be useful. So this result here, that equivalence is decidable, could be useful to formulate some problems and understand their complexity. But in verification, what we really need is an abstract model of programs so that you can throw away some irrelevant details of the program and compile the program into that model and say automata have that property, but not two-way transducers. So what I'm going to show you is hopefully convince you that the model, the alternative model that we have is an interesting alternative. So I'm going to call these streaming transducers. The reason to call them streaming is that unlike a two-way transducer, this transducer does not store input. So you process an input symbol and you process the input symbol one at a time. So in the context of algorithms, it's like a streaming algorithm. It has finite state controls. What's different is that if you think about Mealy machines, what's happening is that every point you output a symbol, and implicitly that symbol that you produce in a Mealy machine or in a rational transducer is added at the end of the output you have computed so far. So I want to make that explicit. So these are going to look a bit like programs, where finite state programs, where the program has. So in this example, the program has one variable. It's called x, and the type of x is string over output alphabet. Okay, so x is a string variable, and we are going to make updates to x explicit. So every time you want to add a symbol, output symbol, you add it to x. So here is how delete is implemented. So initially x is empty, so that's the empty string. If you see an A, you keep x unchanged, but that's mentioned explicitly. So in every transition, the transducer reads an input symbol and updates the string variables. So here x is left unchanged. If the transducer reads a C, x is changed to xc. So this by default is concatenation. So it's just like a string operation. So here C is added at the end of x. B is the operation is the same. B is added at the end of x. And when the string ends, the transducer outputs x. Okay, so x is the output variable here. So it's kind of obvious how this program works. What about reverse? So now for reverse, so I'm going to use the same framework, except when we do updates to strings, the string variables, we no longer require that you add symbols only at the end. So for reverse, you add symbols to the left. So the transducer for reverse is pretty simple. If I read A or B or C, x is updated to the symbol that I read, followed by x. Okay. So the right-hand side is basically a concatenation of output symbols and variables. Okay, of course, if I want to reset x, I could just set x to A, and that would mean that the value of x so far has been lost. Okay, if I want to carry over that value, then x would appear on the right-hand side. Okay, so I have a set of string variables. On every input symbol, the variables are updated. The right-hand sides are obtained by using the existing variables. So why do we need multiple variables? So suppose I want to say that if the input ends with B, then delete all A symbols, else reverse. Okay, so in general, think about if the input satisfies some property, compute this function, else compute some other function. Now, you don't know whether the input satisfies the property or not. I don't know a priori whether the input ends with B. But so the way a two-way transducer would do this is by storing the input on the tape, reading the whole input, figuring out whether the input ends with B, and then applying the right function. How would we do it in a streaming setting? Right? So I want to compute this function. I'm not allowed to store the input. So the solution is kind of obvious. You compute alternative outputs. So in this example, I need to compute two outputs. I need to compute an output that corresponds to delete all A symbols. I need to compute an output that corresponds to reverse. And I use finite state control to figure out whether the input ends with B or not. And depending on the property, when the input ends, I either output one or the other. So in this specific example, the variable x at any point in time equals the reverse of the input so far. Y equals the input so far with all A's deleted. And we have already seen both these examples. So here those updates are similar. So for example, for x, if I read an A, x is updated to AX. If I read a B, x is updated to BX. If I read a C, x is updated to CX. The updates to Y correspond to deleting A. So for example, when A is read, Y is kept unchanged. Okay? So since I have multiple variables, the assignments are so the assignments need to specify how x and y are changed. So this says that on A, set xy to ax comma y, which means set x to ax, set y to y. And how is the state changing? So the transducer is in this state if the string does not end with b. The transducer is in this state if the string ends with a b, which is really the simple two-state machine that you draw to test the property whether the input ends with b or not. So you need a binary state to keep track of this property. So if the string ends here, the transducer outputs y. If the string ends here, the transducer outputs x. Okay, and it starts here. Initially, both strings are empty. Okay, so that's how. So you can use multiple variables to implement regular look-ahead. So we also allow concatenation of variables. So here is here is a simple example. So where what we want to do is that repeat each b as many times as number of a's since last b. So for example, here look at this block AAB. So I want to transduce this to AABB. So the number of times I want to repeat b is equal to the number of a's I have seen so far. So this block here AAAB gets transduced to AAABBB. This b gets mapped to epsilon because there was no b, there were no a's between this b and this b, and this a is left unchanged. Okay, so that's the function. So I'm using this example to show how concatenation works. So we use two variables, x and y. Every time I read an a, I add a to x as well as a b to y. Because so we want to do this in one pass. So we want to do this in a streaming manner. So basically, as I'm reading a's, if I'm reading 3 a's, I want to produce a chunk of output which is 3 b's. Because later when I see a b, I want to add 3 b's. So I want, if I'm reading n a's, the next time I read a b, I want to add n b's. So what's happening here is that the number of a's is collected in x, the number of b's is collected in y. So every time an a is read, we add a to x and a b to y. And when we read a b, we set x, which is going to be the output, to xy. So for example, if I start, first time I read an a, x will be a, y will be a. When I read the next a, x will be AA, y will be BB. When I read a b, now x will be AA, BB, and y will be reset to epsilon. Okay? So since y is reset to epsilon, so as we start reading this block of a's, the a's will be added to x. If I read 3 a's, y will become BBB, and when I read a b, that block of b's will be added to x. So this, so it's actually a compact transducer which implements this. But this shows that x here is being set to xy. So on the right-hand side, so now we can have variables, we can have symbols added to variables, but we can also have a concatenation of variables, x set to xy. So suppose I want to implement the following transduction. I want to map an input word w to ww. So how would we do that? So we will keep two variables. Every time you read a symbol, you add it to both the variables. When the string ends, your output would be xy. So x will be equal to w, y will be equal to w, and our output will be ww. So you do need concatenation. But there is, so the real challenge is to make sure that you have enough expressiveness so that you can capture two-way transducers. You don't have too much so that the equivalence becomes undecidable or you go out of this class of regular transductions. So you need multiple variables, you need concatenation. What you don't allow is reuse. So here is an assignment that's not allowed. So if I'm setting x to xy, like here, I'm setting x to xy, but what you can see here is that y is being set to epsilon. Okay? So we call these assignments copyless. So an assignment to a multiple string variables is copyless if every variable occurs on the right-hand side at most once. So this assignment is copyless because x appears once, y appears once. This is also copyless. X and y both appear once, except they appear in the same right-hand side, but y cannot appear again. So this is not copyless because y is here as well as here. So that's now the full model. So here is the definition of the streaming string transducer. So you have a finite set of states. Yeah? Yeah, so you can swap the order, yeah. you can concatenate here. So there is really no restriction on how. So actually, I think the definition. So these were all examples. With the definitions, it would be become more precise. So we have finite set of states. We have an input alphabet, output alphabet, initial state. We have a finite set X of string variables. So these are strings over outputs. There is a partial output function. So actually, transductions typically are defined as partial functions. You could say if the input is this, then I don't really want to output anything. So even for rational transducers, there are final states. But just by definition, they can be partial functions. So the output function is partial, which means if I end up in some state, I don't want to define output. In some cases, I do want to define an output. So this output function f for a given state maps it to a string over B union X. So this is output, X is variables. So for example, X, Y, B, that would be a potential output. The state transition function is like in DFS, given a state and an input symbol, you update the state. We have a variable update function which says given a state and a symbol and a variable, what's its new value? And the new value is given as a string over, again, B union X, right? So output symbols concatenated with variables. Variables can be concatenated with one another. So it could be A, X, Y, B, Z, something like that, if X, Y, Z are your variables. What's the requirement? In these maps, partial output function and variable update function, every variable appears at most once on the right-hand side. Okay. So collectively. So if X and Y both appear on the right-hand side for X, then they cannot appear anywhere else. Okay, so I'm not going to show you the detailed semantics. If you understand the syntax, how to define the semantics is kind of obvious. A configuration would be the state and evaluation for all the variables. So these variables take values over B star. So B is your output alphabet. So those would be output strings. So initially, the machine starts in Q0. All variables are empty strings. When the input ends, you add in some state. If the output function is defined, that would be the output, and you would just evaluate at every step, you just evaluate the string on the right-hand side by plugging in the values of the current variables. Okay, and so this gives you a transduction from A star to B star, so a function from input strings to output strings. To give you a little more intuition, so every time an input symbol is processed, we are adding a constant number of output symbols. So I cannot do X assigned XX. If I can do that, then everything I have computed so far in X gets doubled. And as you can imagine, if I keep doing that, the size can grow exponentially. That cannot happen for these transducers. In fact, the output is bounded. So if the length of the input is n, the length of the output would be within a constant factor of that n. Okay? And the constant is independent of the input length. It depends on the transducer. So it's basically linear. In fact, you can implement this transducer in linear time. So everything you can implement it's a subset of linear time list processing algorithms. You cannot do sorting because just from the lower bound for sorting. The way to think about this is unlike so these outputs. So you are computing multiple outputs. So different chunks are being computed using concatenation. You can rearrange these output chunks, right? But you're not examining the outputs. So another way to think about these is that you have a one-way input tape. You have multiple output tapes, but you are not examining. You're not reading outputs. These are really write-only output tapes, and the operations allowed on output tapes is concatenation or adding symbols and things like that. Yeah. So you can use that to actually show. So another way to get some intuition, this transduction cannot be implemented. If I say, okay, there is a sharp somewhere in this string, and what we want to do is merge this string with this string. So, or another way of saying that is I have two input lists, and I want to produce an output list which is a merge, a step-by-step merge of the two lists. You cannot do that because you need only the transducers have only finitely many variables. So of course, merge can be implemented in linear time, but these these things cannot do that. So if you think about this input, and suppose you want to produce this output, how would a program do it? A program would basically keep a pointer here and a pointer here, and you would move both pointers and then produce the output. So every time you read a symbol, so I want to output one symbol from here, one symbol from here. So I need these two pointers which move in sync. But if you think about basic results in automata theory, if I have a tape with two read heads, then the simplest of problems are undecidable for those. So you cannot have two read heads which move synchronously. So these transducers have only one read head, and you have these multiple outputs, but you are not examining them, and that's how we get all of decidability. You can show that multiple variables are really needed. So in particular, this is the following transduction, that given a string W, I want to output WWW. So I would need 3 variables, and that can be proved formally. Intuitively, it's kind of obvious if you're reading one symbol at a time, and you cannot shuffle them at the beginning because you want to concatenate only at the end. So you need to carry all those 3 variables separately at every step. So in the world of transducers, this pre-post condition problem is called type checking. So I'm given a regular language of input strings, I'm given a transducer, and I'm given a regular language over outputs, and I want to check whether if the input is in L, and if I apply the transduction, am I guaranteed that the output is in the post condition? And that's so that problem of type checking can be solved in polynomial time. So you basically would I'm not going to show you the proof. I'm going to show you a proof of this equivalence in sort of the intuition of why this is solvable. So equivalence given two STTs S and S prime over the same input-output alphabets, we want to check whether they define the same transductions. Okay, so I'm given 2 machines, and I want to check whether they, on every input, whether they produce the same output or not. Okay, so this is actually tricky because if I give you a transducer, and if I ask you the question, can the transducer reach a state where 2 variables x and y are the same? Okay, the 2 string variables have the same value. It's very easy to see that's basically Post's correspondence problem, and it's undecidable. So with variables, if you remember, if you have done this, if you know this Post correspondence problem, you have these strings and you want to concatenate them. So the moment you have string variables and concatenations, things can become undecidable very easily. Let me show you why the equivalence is decidable. So the first step is basically, so I have 2 transducers. So here is the transitions of one transducer. Here are the transitions of another transducer. This transducer has variables x, y. This transducer has variables x prime, y prime. And these are I've just picked two transitions. And I want to check equivalence, I need to simulate them simultaneously. And how to do that is kind of obvious. So what we do is we take product state, just like product of automata. So, then we make sure that the input symbol fed to both these states is the same. So you synchronize transitions on the inputs. And then you say, okay, so this combined machine has now 4 variables, x, y, x prime, y prime. You make sure these names are different from these names. And then these are just updates to these variables. Okay, so that's the first step. So you search in the product. So here's the second step. So now I want to see if the 2 transducers are equivalent or not. So one way to check is that to guess or to detect, to look for an inequivalence. Okay? So I can do it for every, so this we are going to check this for every step. So we want to check if the transducer ends here. And here is the output function of the first, here is the output function of the another, right? And x, y are variables of one, and x prime, y prime are variables of the other, right? And we want to check if these values are different, okay? So how do we check whether these values are different or not, right? So so we can't really run that test. So we are going to guess for the kind of difference that you see, right? So here is one possible difference. Say that there is a bit in f and there is a bit in f prime which differs, right? So and let's say that bit is at distance the length of x from in f. So so here is one possibility that y prime is composed of 2 strings, u, v, and there is a b somewhere, such that this a is different from this b. What this means is that the length of x is same as the length of x prime followed by this prefix of y prime, which is u. So if y prime is of the form u, b, v, with the length of x equal to length of x prime u, then the two are different. So basically they differ on a bit, and the bit is this particular a. So that's the guess that's being done. So we are guessing for a bit that's different, and we are saying, okay, oh, the bit that differs is this particular a here. So still, of course, we are, so that's, and there are only finitely many guesses, and in fact, in the final machine, it just would correspond to different potential initial states or final states, something like that. So here is but the key to the proof, right? So how do I make sure that this difference is the right one, and how do we propagate that? So one way, so this is how we can do it. So we are guessing that the two outputs are different by saying that, oh, there is a bit in y prime which is b, and that b is at the same distance as this a in f, which means the length of x is same as x prime followed by the prefix of y prime where that b is. Right? So we can use that information to classify variables into three categories. L means the variable is contributing to the left of difference. So for example, in f, we are saying this a is the differing symbol, right? So x is contributing to the left of the difference, right? Y is not contributing to the difference at all, because y it's in the suffix, it comes after the difference. In f prime, x prime is contributing to the left of the difference, but this y prime is actually, the difference lies in the middle of y prime. So that's why the classification of y prime is m, which means that the difference is contributed by the value of this variable. So we need these three classifications for variables: left, middle, or don't care, because this is not contributing to the difference. So our algorithm is going to be track this classification LMD for all the variables, and make sure that this length requirement is enforced using a counter. Okay, so this abstraction basically says, okay, let's get rid of all these assignments to variables. Let's replace them by this finite state information, which is just classifying variables into these three classes. And for this example, x is left, y is don't care, x prime is left, and y prime is middle. And now the key to the algorithm is, if I have this classification, and if this was our assignment, I want to compute what would be the classification here. So now here x and y are getting switched. So what would happen is that the classification of x and y would be switched here. So in fact, this classification can be updated consistently going backwards. But you can also do it going forwards by defining a non-deterministic machine. But the basic idea is, when is the classification here consistent with the classification here? And when we guess the difference, we know that the classification actually contributes to the difference. So if I look here, that x prime is contributing to the left, and here x prime is being set to ax prime y prime. So here the classification for x prime y prime for both is going to be left, because here x prime contributes to the left. So whatever the value of x prime and y prime was here, it would contribute to the left of the difference. And the final thing is to making sure that it's the length assumption is really checked, because if we go back here, what I really want to check is that this length is equal to this length, which means the number of bits contributed to the left by both are essentially the same. So that's done by introducing a single counter, and so here we are adding one symbol to x, so that's why there is one increment. So whenever s adds symbols, we increment. Whenever s primes add symbol, we decrement. Okay? And since here the classification of both x prime and y prime is left, we add two decrements. Okay, so it's basically, so this is, I guess, was a bit hurried, but maybe hopefully you got at least some idea. This is just a summary. So we are going to build basically a non-deterministic one counter machine, where the finite state keeps track of the state of s prime, and then the classification of string variables to these three values. So as you can see, it's polynomial in the in the number of states. It can be exponential in the number of variables, because for all possible classifications you get a state. The basic idea in transitions is you make sure that the two transducers are reading the same symbol, so you are feeding the same input to both. You need to update the classification consistently. So you are replacing the assignments, you're abstracting the assignments to these classifications. And to make sure that the difference is actually the real difference, you need to add increment decrement to this counter. So what basically we are checking is that the number of bits S adds before the difference is same as the number of bits S prime adds before the difference. And we can't really keep track of the actual strings the two compute. So, but to check inequivalence, we don't really need that. And the complexity is of formally p space, but it's basically polynomial in number of states and exponential in number of variables. So what about expressiveness? So of course, the nice result is that this is an alternative characterization of regular transductions. But basically, the result is that you can simulate two-way transducers, one by a single left to right pass if you have these multiple variables. And the expressiveness is not too powerful if you restrict to these copyless assignments. So the STT definable transductions is MSO definable. So this is how this proof goes. So I'm not going to show you this proof. This was already proved by Engel, Fried et al. That MSO definable transductions can be captured by two-way transducers. And I'll give you a brief hint of how how does this proof go and what's the challenge that an STT can simulate a two-way transducer. So now these regular transductions have some nice properties like composition, regular look ahead, which follow from the properties of this class. But the good thing about these transducers is that you can actually get direct constructions. For example, if you want to show automata are closed under some operation, you don't say, okay, because regular languages are closed under operation. You give a constructive proof, and so you can actually construct automata for the intersection and so on. The same things are possible here because the model is quite intuitive and simple. So here is what's going on with two-way transducers. So actually, some of you may have seen this proof. Well, 30 years ago in automata theory, course was more challenging, and people would do these proofs like, okay, two-way automata are same as one-way automata. People no longer do that, but the proof is actually not that hard. So let me first tell you about why are two-way automata not transducers. Acceptors can be simulated by one-way automata. So what you do is intuitively what you say is, okay, here is my input. A two-way automaton is going to go back and forth. Let me see a particular line here. So having read this prefix, what should the one-way simulator remember? So it needs to summarize all potential computations of the two-way transducer. So it needs to think about what happens. What happens if the two-way transducer was doing a backwards pass starting in state Q, but you have finitely many states Q. And that's why you need to worry about only finitely many backward passes or boundedly many backward passes. So for each state Q, you want to ask the following question. If the automaton was going backwards in state Q, what would be the state it would go forward on its reversal? Right, basically. So if it's going backwards, it would reverse. Maybe it will go back and forth multiple times. But with respect to this fence here, the only thing you care about when it crosses this fence, what would be the state? And that can be captured by a function from Q to Q. It says that if I start in this state, what would be the state that the machine would go back in while crossing this edge again? And then you have to update this information consistently, because the one-way transducer is going only left to right, and it's trying to compute this mapping from Q to Q, and at every step it updates that mapping. Now we have transducers. So what would happen is that the two-way transducer on this pass would have produced some output. But we have multiple variables. So what we could say is, let me introduce a variable called xq for every state q. And when I'm here, when the one-way transducer is here, it expects that the value of xq is what the two-way transducer would have produced, going backwards in state q and doing this pass, and when it crosses this boundary again. And that's sort of a natural generalization of the proof that two-way acceptors are same as one-way acceptors. Okay, but what you have to show is, well, the value of this xq can be updated consistently as you take one step. So let's see what goes on. So suppose currently I'm processing a symbol A. And so by this inductive hypothesis, what we know is that I know the information that if the machine was going backwards in state q, it would end up in this state f of q, and during that process it would compute, whatever it would compute, it's stored in the variable xq. Right? And if I read a symbol A, now I want to ask the same question because I want to update the information. So for a given state u, I want to find out what state would I come back if I go do this pass. Well, so to state u, we feed the symbol A that says that, okay, here you would be in state q. So we have inductively computed the value f of q. So to f of q, we can apply a going forward relation on symbol A, and that would be the state. That would be the updated value of f of u here. So this is the state you would end up in if you started here. And what would be the value of xq? The value of xq will be whatever the two-way transducer produced from on this transition, the value of xq followed by whatever the two-way transducer would produce on this forward transition. So it would be the string here followed by xq followed by the string here. And we have a concatenation, so we could say, okay, we can easily do that. But the problem arises because there may be another state v which goes to the same q, because going backwards, the machine is not really deterministic. So, well, it's deterministic, but it's two states can map to the same state. So the forward image is deterministic doesn't mean backward image is deterministic. So then f of v, or the value of xv and xu, both would have to reuse xq, but reuse is not allowed, and that creates problems, and unfortunately I don't have time to show you how that works. But intuitively what you have to do is to do a careful analysis of sharing, and you can't really just store these values of xq directly. You have to store them somehow symbolically and make sure that you are updating that information consistently and in a copyless manner at every step. Okay, so in the next 10 minutes, I'm going to tell you that, okay, so why, going back to these programs, that why are we interested in this, right? So, okay, so what if this streaming transducers have the same expressiveness as two-way transducers? It's, so I think the one plausible reason to be excited about this is, well, one is that, okay, you can do it actually going left in a single pass. But the other thing is that we have found a very nice class of heap manipulating programs, and this gives the first set of decidability results for actually for any class of heap manipulating program. So what's this class? So here is how a program looks like. So it's a sequential program, and the heap, the data is stored in this heap. So you have the cells hold a data value and the next pointer. The programs can have Boolean variables, they can have pointer variables, and so on. So the key is how do we represent the heap, right? So so here is how a typical program configuration may look like. So here this program is trying to insert some cell into this list. So if you remember how you write these programs, you know, there would be like a prev pointer which is pointing to the previous cell, a current pointer which is pointing to the current cell. You create a new cell, and what you would do is to change the next pointer of new to current. At some point you would swing this next pointer of prev to new. So the general configuration looks like the program has a finite number of variables which point into this heap. The heap may not be a list because, in fact, in general, it looks like a forest or a tree. And what the program does, it can add cells, it can change next pointers, and it traverses the heap by following next pointers. So what we want is, I mean, given all this wealth of undecidability results, we want to understand now not what class of programs is decidable, but now we change the question. We ask the question, how can such programs implement regular transductions? So most operations, insert, delete, reverse, and so on, are regular transductions. So what's the restricted class of programs whose expressiveness would match regular transductions. And if we can find this, then the equivalence and a lot of analysis problems would be decidable, because problems are decidable for streaming transducers. So, okay, so this is what I really wanted to show first. So so this is the answer. So in the regular heap manipulating programs, the updates that we allow are x.next is y. So x is a pointer. So this is updating the next pointer. So this changes heap. X assign new a, which is adding a cell to the heap. So you can update the heap destructively. Traversal. So current is treated as a special pointer. So initially current points to the beginning of the input list. And we can traverse the input list because that's essential. So current is assigned current.next. But what we disallow is x assigned y.next. So you cannot traverse because, again, going back to automata, if I have an input tape and if I have 2 read heads, and if I move them, then things are going to be undecidable. So if I've stored that as a linked list, and if I have 2 pointers, and if I can advance both pointers, then I'm going to be in trouble. And that's why that's the reason why all previous results are about undecidability. But I'm going to convince you that in fact you don't really need this, because even without this, you can implement all regular transducers. Of course, that limits the expressiveness, but for a large variety of programs that people write, they don't really use this. So if you go back to this configuration, the pointer that I would really want to advance is current. Right? And then I can set prev to current, that's allowed, but I don't really need to examine the next of prev. I'm going to update prev to current and current to current.next. That's how a typical program works. Okay. So let me give you a brief hint for why this theorem holds, that so the theorem is that the programs of the above form are equivalent to this streaming, the streaming transducers, and here is a brief intuition for why it holds. So given a heap like this, I want to represent it. I want to simulate this by STT. So the STT, of course, doesn't have cells and next pointers and so on. So how can it represent this heap? So what it does is it abstracts this content in string variables. So I have some interesting nodes, which are like the nodes that these pointers directly point to, like x, y, and z. This node is also interesting because it has 2 predecessors. Okay? So, but if I look at this sequence, or the sequence of these 3 cells, so that's not really important anymore. So I'm going to store this content in a variable called u1. Because I cannot set x to x.next, so I cannot really traverse this. So I want to treat these like output variables in my SST, in the streaming transducer, because the decisions are not going to be based on what the content of this. What may happen is that things may get concatenated, or what may happen is that the next pointer of x may be updated to z, in which case all of this part would be lost. So that's sort of the intuition. So what we do is in this streaming transducer, we remember the shape. So we say that x is basically the string u1 followed by string u2 followed by the content of z. And z itself is, well, the string u3. Okay? So anything along a sequence or a chain of cells that do not contain a special node, they get compressed into a single string variable. And if the program does an instruction such as y.next equal to z, so what would happen? So this next pointer is being swung to this. So our heap would look something like this. And now what happens is this chunk becomes irrelevant. So I drop this variable. I also concatenate these two because we want to maintain this invariant that the heap only special variables separate cells. So this u1, so we can do that by concatenating two variables. So previously there was u1 and u2. I'm just going to set u1 to u1.u2, or concatenation of the two, and that would remember this whole chunk here. So basically the contents between special cells are kept in a single string variable. The number of special cells can be bounded, and that that's the sort of the intuition why you can represent the heap in using a finite number of these output variables which never get examined. So I'm going to wrap up in like 5 minutes. So just so if you really are interested in analyzing programs, finite alphabet is not really a good abstraction. So what we really have for program verification is an unbounded data set. So for example, these lists may be storing names, and you may want to, the list is sorted and you want to insert a given name. So that may be a typical program. So the moment you have unbounded data, you need to restrict the operations on data if you want to get decidability. So what we do is that the data set supports equalities test and ordering. So it's a set of ordered things, but there is no arithmetic being performed on this data. And then so you have to generalize this model so that you can actually talk about these data elements. So these programs have data variables also. So we have a paper in POPL next month, and all the details are there about this, the program verification. The only tests that are allowed are equality and less than. You also want to allow input-output values to these variable to these functions, and it turns out that things are still decidable. You can do things like check if the list is sorted. You can't sort the list, but you can check if it's sorted. You can insert an element in the sorted list. You can delete all elements. You can reverse, and you can do a variety of these things. So this is how a program so we have defined a specific syntactic fragment. This is how the program looks like. This is exactly how you would write a C program to say remove all the duplicates of this input data value v from the list pointed to y current. So here there are two inputs, a list and a data element, and you want to delete all occurrences of this data value from this list. And so it's doing pointer manipulation like a C program, and all these questions are decidable in P space, which is assertion checking. Here, if I want to check that if I'm accessing this current, then this current should be not nil. So, so null pointer dereferencing. I could check whether two things point, because this really compiles into a streaming transducer. So if you have an alternative specification by a streaming transducer, you could check equivalence and see if they're doing the same thing. So to summarize, so what I've shown you is actually a new model for computing, for doing string transductions using multiple string variables, so that you compute different output chunks at every point and rearrange them as you go along. And the key to expressiveness is having this multiple string variables and ability to concatenate them, rearrange them. And the key to having decidability is to make sure that the updates are copyless and you are not examining the output. You don't have pointers, or you don't have traversal over the output chunks. So it's really like write-only output. Okay, and the problems that are decidable are like equivalence and type checking. It's the expressiveness is very well characterized. It's using these two-way models, and there is potentially interesting application to program verification because we have identified this class of programs. I'm actually quite excited about this work, and we are exploring a variety of directions. In particular, what happens if you have tree structured data. So for, again, XML processing, you have like a hierarchically structured data. Now, there are models like macro tree transducers and attribute grammars which can transform XML data, but they don't do it in a streaming manner. So they are inherently declarative. These formalisms are not closed in the regular look ahead, and they basically construct the parse tree, and you have to process the parse tree by going up and down. So for querying, people have thought about streaming models, but not for transducers, and we have some nice results for that. Learning is actually another interesting question. So for two-way transducers, it's hard to think about problems like minimization and learning from examples. Now the state has a clear characterization, and we can hopefully apply some of the insights about rational transducers, about finite automata, to get some nice theory of minimization and learning here. And the reason to think about minimization and learning are really these two applications. So So for example, in Excel, people provide these macros. And so the big thing in program synthesis now is, can one learn these macros to allow end users to program, where they would program just by giving examples. So you would say, okay, I want to transpose these columns. I want to take these, this is, given a name, I want to, Rajiv Allur, I want to transpose it to Allur Raju. And you would just show that by an example, and from that you want to learn this. And this is a big thing in program synthesis now, how to make the macro generation automatic. And people have been trying to use transducers, but most of the techniques are ad hoc, and we think that this theory would actually make that a lot more systematic. And similar application is actually this sanitizers for strings. So a lot of security attacks are basically you type in some URL, right? But in that URL you embed some text. And so what the sanitizer does is it's really a string processing. So you take that what's being typed and you sanitize it, you make some checks and you transform it. Again, it's, of course, people write programs to do that, but unlike, say, things like document processing, there is no clear theory for that, because, so I think if we can solve this minimization problem, which is actually seems to be quite hard, but possible, I think we would be able to attack these problems. So thank you. Actually, so from that book, The Art of Multiprocessor Synchronization, a large number of programs implementing for operations on lists fall within this class. Now, it's possible that if you just pick up some random list processing program, it wouldn't fall into this class. But if you look at what the program is trying to compute, except for sorting, it turns out to be a regular construction. So the thing is that people, okay, so for example, the traversal, you don't really need to traverse. If I have a prev pointer here, I don't really need to traverse that list. I really want to traverse current, right? But maybe the program is written where it says prev is assigned prev.next because the programmer has this invariant that prev.next is equal to current. To fit into our framework, the programmer has to say prev is assigned current and current is assigned current.next. So I think the way I view this is if we can build tools which analyze these programs, that's an incentive to write programs in this particular fragment, unless the function you want to compute falls within this class, outside this class. So of course, I mean the expressiveness is well characterized. And another potential thing would be to use these as, say, invariants or as some abstractions of programs. So it's an open question, but that's our hope.
So far, you don't have like some kind of semi-algorithm that sort of.
No, this is actually very new work. In fact, this is the first talk I have given on this topic, and so it remains to be seen.
So one more question. So is it? Are you aware of the connection, like any connection at all, between your work and the works by some people who try to relate like list manipulating programs with counter automata?
Yeah, so there is, I can answer that offline. Yeah, there is actually applications of even tree transducers, and but that application is quite different. I can, like the work by Bujani and so on. Yeah, there is, I can tell you that offline. Yeah, it's a long story. Yeah.
One more question. So the flow insensitive alias analyzing over scalar variables decidability is open. Does this have any?
So the thing, right? Yeah. So the so for I think in this literature on program analysis and for aliasing problems, all results are really about undecidability. So there is, in fact, a couple of years ago, there was a stronger result than the one that you mentioned by Ramalingam, which shows that May aliasing for a very simple fragment of programs is undecidable. So, but the thing is, so we have a different fragment, basically, right? And for this fragment, aliasing is decidable. It's actually context sensitive, flow sensitive, aliasing is decidable. And this wasn't the fragment considered by people earlier, because I think it's really this insight that, okay, you don't need x assigned y dot next. I mean, we came to that just because of this model, right? Yeah. So it's not something you would think of as a restriction on programs. Yeah.
So I noticed that somewhere garbage collection information came to the algorithm. So maybe
Oh, that.
develop a kind of theory of giving directives to the compiler as to where you can that.
Right. So here, yeah. So actually, so this stretch here to on the bottom, yeah, that becomes unreachable, and that's why we can compress, right? So I think if the program falls within this class, we can do very powerful things, because the state of if you view it as a transducer, then the underlying state is really captured by this shape, which says that which segments follow each other, and then the contents of the shape, which are stored separately. And the shape is finite object, and you can run any graph algorithm on that, find unreachable things. So it's possible, yeah. Yeah. You can have strings, yeah. You can have strings. As I said, so more technically, if I give you an STT, I give you a location, and I give you two variables x and y, and I ask, is there a computation of the STT which goes to that location with x equal to 1? That's undecidable, and it's the same as the PCP problem. I mean, the encoding is like trivial, right? And if I ask the question, can I get there with x different from y? And that's actually exactly the same as the equivalence question, because if I take product of two STTs, in the end, you just want to check whether the outputs are different, and that's decidable. Because basically, you guess the difference, and and then you just make sure that the bit that you're guessing, the distance of that from both the STTs have added exactly the same number of bits, and that you can model by a single counter, yeah. So it's, there are like depending on which question you're asking, things are a bit subtle, yeah.
You mentioned non-determinism is ongoing, but is the merging completely devastating to this theory?
Yeah, no, I don't know. So there is some work on non-deterministic. So the interesting thing is that this equivalence between MSO and two-way transducers doesn't hold for non-deterministic ones, and we think that it holds for the non-deterministic versions of that. But yeah, that's it's work in progress. It's a conjecture at this point. Yeah.
Okay, so let's thank the speaker once again.
Welcome to the second invited talk by Sampash Vaidpala. He did his undergraduate studies at IT Delhi. He continued with a PhD at CMU under the guidance of Avrim Lam. He has earned various awards, including a Sloan Fellowship and a Guggenheim Fellowship. He has visited the University of California in Berkeley, and he was a visiting researcher at Microsoft. He has had a faculty position at MIT for 9 years before he moved to Georgia Tech, where he is a distinguished professor. He's also the director of the Algorithms and Randomness Center and think tank at Georgia Tech. His research includes theory of algorithms, learning, data mining, algorithmic geometry, and randomness, and most recently spectral algorithms. The web page of his school characterizes him as by saying he gets unreasonably excited when a phenomenon from one perspective turns out to be simple from another. Today, he will talk about recent progress and open problems in algorithmic convex geometry.
Thank you, Martin, and thanks to Meena, Kamal, and the organizers for this invitation. I remember in the 90s when I was excited to be bringing speakers from the airport and listening to their talks and realizing that this is what I wanted to do, so it's great. And after that lunch, I briefly considered singing a lullaby to help you rest, but given both my skills and the chance that I'll fall asleep, let's stick to some math. Okay, so this talk is meant to be a survey. Please interrupt, ask questions. Hopefully, you'll find some of it very interesting, and if not all of it. Okay, let me begin. So what do I mean by algorithmic geometry, or what do we mean? So it's the study of computational problems and how their complexity grows with the dimension. And although we say geometry, really, you can take anything and view it as geometry. So in a typical setting, the dimension is just the number of variables in your optimization problem or in your state machine or what have you. And so that's the direction. Now, just to understand how geometric structure can play a major role in what the complexity is, here's a quick example. So the first version of this problem, you're given a matrix explicitly n by n, and you want to know if the entries of this matrix can be viewed as inner products of a set of n vectors. So do there exist vectors so that the entry aij is the inner product of vi with vj? So in other words, you're checking whether the matrix is semi-definite, and we know this can be done in polynomial time. Ignore it. Now, very closely related question is, given a set of vectors, does there exist a rotation that puts all of them in the positive orthant? Now, this actually is almost the same question, except it requires, so semi-definiteness is being able to factor into a matrix times its transpose, so its inner products, every entry is an inner product. And this is asking for the same thing, except it also wants that every entry of this matrix or every vector is non-negative. And whereas the first problem is polynomial solvable, this one is NP-hard. And the difference, one difference, is that the first one is actually a convex problem. The set of possible solutions forms a convex set. And the second, we don't know of a way to view it as a convex set. So convexity seems to be a metaphor for structure that allows polynomial time or efficient solvability in the geometric setting. And this is what I'll try to consider from various perspectives through the rest of this talk. Okay. So a historical note, there were, I think if we had to pick out two milestones, there were two that happened in this field that also influenced the rest of theoretical computer science in a profound way. The first was the discovery of the ellipsoid algorithm, formulated by, or stated by Yudin Demirovsky, Shor, and then proved to be polynomial for linear programs by Katian, whose name I've managed to misspell. And then following this, there were these great consequences for discrete optimization. So you know how to, say, find maximum cliques in perfect graphs, or minimize submodular functions, and so on, by just viewing them as convex optimization problems. And the second milestone was the discovery of an algorithm for computing the volume based heavily on being able to sample random points from convex bodies. So in both these settings, optimization, so that problem, that algorithm solves the problem of optimizing a linear function over a convex set, and this one computes the size of the set. Again, the set is convex, polynomial algorithms, and yeah, they're okay. So here's the outline of my talk. So I'll begin with some properties implied by convexity. Just a quick sample of some of the more basic ones that seem to play a major role. And then we'll look at 5 fundamental problems which are all hard, intractably, impossibly hard in general, but efficiently solvable, at least in some general settings, with the assumption of convexity. And then some algorithms, reductions between these problems, for these problems. And finally, a note on what one might hope to be able to do beyond convexity. Okay. So I tried to be somewhat comprehensive in the survey article that accompanies this talk, and thanks again to the organizers for encouraging that. But feel free to interrupt me with any clarifications. So convexity. So here are various levels of convexity. So by a set being convex, we just mean, of course, that if 2 points are in the set, then the line joining them is in the set. Right? So the indicator function of the set is convex along every line. Now let's move to functional generalizations. So that was a 0, 1 function. Set 1 in the set, 0 outside the set. Now you go to concave functions, where the value of the function between 2 points is a concave function of the 2 points, so it's at least the average, the same average as the points form. Log concave, so weaker assumption, you can think of it as this geometric average, or the logarithm of the function is concave. So you get more general class. Quasi-concave, where all you require is that the function in between is at least as large as the endpoints. So in particular, if I take any level set, function value at least t, that set is convex. So every level set is convex. And finally, an example of a class that's not convex, star-shaped sets. So whereas for convex sets we require convexity along every line, for star-shaped sets you require convexity only along lines through a fixed point. There's one point, a center. Every line through that point must be convex. So you get shapes like that. So if you want to play with examples in your head or on paper, here are prototypical classes. Okay, now here's some structures that we can expect once we make convexity assumptions. The first one about a set is the existence of a separation oracle. Okay. To have efficient algorithms, we need good characterizations, right? We need to be able to say yes or no for the decision version efficiently. So the membership question, does X belong to the set? Now the set itself might have a very complicated explicit description, but if it's, at least if it's outside, you're able to certify that it's outside with a hyperplane. So a short certificate that one half space contains the set, the other half space contains the point. So that's one certificate. It's a good exercise to prove that this always exists for a convex set if you haven't done it. Second is how points are distributed. So the volume distribution of points in these sets or in distributions that have convexity-like properties. So for this quick definition, the Minkowski sum of two sets is just the set of all points you would get by taking a pair of points, one from one set and one from the other. So if you added a circle and a square, you'd get that rounded square, or squared circle, whatever. There's a nice volume inequality, a classical inequality, which says that the volume to the power 1 over n is a concave function. Okay. And now why is this interesting? So this is just for arbitrary sets. They don't have to be convex. They just have to be bounded measurable sets. Why is that interesting for the convex setting? Because let me consider two sections of a convex body given by intersections of the body with hyperplanes, say. So you have a section at x and a section at y, and I consider some section in between them. Now that section can be viewed as a Minkowski sum of these two sections. It's an average, every point on there is an average, and therefore the volume of the intermediate section to the 1 over n is at least the average of the two volumes to the 1 over n. So you can't have volumes go down and up again. They have a nice distribution. In fact, the distribution is log concave, but it's 1 over n concave. There's a functional generalization of this called the Perkopa-Leinler inequality, and it says that suppose you have three functions, f, g, h, non-negative real valued in n space, and h at any point is the geometric average of f and g. Okay? So it satisfies the log concavity style condition. Then the integral of h is at least the geometric average of the two integrals. Okay? So if I replaced in this convex body by just some function in space that satisfied a relationship like this, then you'd have that the integrals, as you look along cross sections in some direction, would behave in this modulated way. They can't just drop and go back up. Once they start dropping, they have to keep dropping. Okay, that's second structural aspect. One more, sandwiching. So, or rounding. A classical theorem of John says that for any convex body, there's an ellipsoid so that that fits inside, completely inside, and you scale it up by a factor of n, the dimension, so independent of the body, and that will now contain the body. Okay. An alternative and algorithmically tractable rounding is the following. So for any distribution with bounded second moments, so that nothing goes to infinity, so for example, the uniform distribution over a convex body, there's always an affine transformation that makes the expectation, so if x is a random variable with the uniform distribution on a convex body, we can always arrange it so that the expectation of x is 0, so that's just a translation, and the expectation of its covariance is the identity, and that's the scaling. So there's always an affine transformation that makes the body isotropic. Okay? Now what's nice about this position is the following theorem of Cannon, Lovász, and Szymanowicz, which says that in this position, the body is sandwiched between two balls. B just stands for the Euclidean ball of unit radius, of radii that are off by exactly a factor of n. See, the left radius and the right radius are factor of n away. So it's the same sandwiching as that, same factor, but completely different construction. Okay. In fact, one way to construct the John ellipsoid, define the John ellipsoid, is the maximum volume ellipsoid contained inside a body. This one has nothing to do with maximum volume. It has the same factor. And this, as we'll see later, can be constructed algorithmically for convex bodies. Okay, so those are three structural properties. Now here are the 5 problems. Now, I'm going to talk about 5 problems. You can choose to listen to only one whenever it comes up. Feel free to, or 2, or hopefully more than 0, but it's up to you. So optimization. You have a function, and so we're looking at the abstract versions of these. Really, each problem is an area. I mean, the special cases are very interesting, and there's lots about them that I'm not revealing, so on. So there's a function specified by an oracle, so you can query it. What is the value at x? You'll get back the answer. You're given a point x, where the function value is bounded, and an error parameter epsilon. And the goal of the algorithm or the problem requires you to find a point y so that the function value at y is almost the maximum, is nearly maximum. So for example, linear programming. Problem 2, integration. So same input setting, exact same input setting, except now I've assumed the function is non-negative everywhere. And you want to find a number, a real number, that is a 1 plus epsilon relative approximation of the integral of the function. So we assume the function has a bounded integral. Okay? So this generalizes the problem of estimating the volume, where the function would just be 1 in the set and 0 outside, and then the integral is just the volume. Problem 3 is sampling. And here again you're given a function, a point with bounded function value, and an error parameter epsilon. And what you'd like to output is a point y whose distribution, so it's a random point that you're outputting, and the distribution is guaranteed to be close, and there are various notions of probabilistic distance, so let's just say close for now, to the distribution whose density is proportional to f. Okay? So I might not know the density, exact density at a point, but I know what it should be proportional to, and I'd like to output a point with density proportional to that. So for example, if you wanted to output a point that's uniform in a convex set, you just want that the density is nearly constant. Doesn't matter what the actual density is. For that, you would need to know the volume, but we don't need that in the input. Okay. Problem 4, rounding. So you want here, we think of rounding as an affine transformation that, I'll say more about this later, but which tries to put the function in a round position so that the function at large values contains a large ball, and the function, most of the function lies inside another ball that's not too large. Okay, so it's sandwiched between two balls, just as we did for convex bodies. And finally, learning. So you're given points that are independent and identically distributed from a distribution that you might know, or maybe it's unknown, depending on how general the problem, and an error parameter epsilon. Now these points are labeled 1 or -1, or positive or negative. So you're given points, labels, and your goal is to come up with a rule, an efficient rule, so that if somebody gives you a new point from the same distribution, you can label, the rule is a function that maps the point to 1 - 1, and is correct on 1 - epsilon of the distribution. Okay, so it correctly labels almost the entire distribution. That's the learning problem. Now this generalizes integration in the following sense. To compute the integral, you have some set and you just want to know the sum of the function. What is it that defines the set? Whereas learning requires you to actually learn the boundaries of the set, so that you need to be able to answer correctly whether you're in or out. And if you can do that for most of the set, then you know not only its volume, you know almost every function of the set. So it's more general in that sense. Okay, so now I'm going to launch into a few algorithms and reductions to see why these problems are tractable in the convex setting. Okay, so optimization. So here's a very simple algorithm for optimization. You have a convex body K, and you have a function f that you're trying to maximize, say. So you find the centroid, the average of all the points under the uniform distribution. Restrict the set to that part of it where the function value is at least the value at the centroid. Okay. Now, if the function that you're maximizing is concave, then this restriction is itself convex, and therefore you still have you intersect a convex set with a convex set, and you still have a convex set. Okay. And actually, all you need is that the function be quasi-concave. Its level sets are concave. So the function value, at least something, is a convex set. And you repeat. Now, why should this be a good algorithm? You'd like to make progress, and you want to quickly get to the optimum or a near optimum solution. And a classical theorem of Grunbaum, which I haven't stated here, states that if I take a convex body and I consider a half space that does not contain its centroid, then it has that contains its centroid, then it has at least 1 over e fraction of its volume. So the volume, if you make any hyperplane cut through the centroid, doesn't go down as half, no, but no worse than 1 over e. So that sounds like great progress, because very quickly your volume will become exponentially small compared to what it was to begin with, and then you can use that to bound how far you are from in function value also. The trouble is that computing the centroid is sharply hard, even in an approximate sense, for deterministic algorithms. So how about we just sample random points, take their average? I mean, the centroid, after all, is the average of all the points. We'll sample, take their average, and do this. And so a simple generalization of this Grunbaum theorem is the following. If I take m random points, take their average, and make any hyperplane, any half space that contains the origin, that contains the centroid, then the volume of what's left is at least, in expectation, 1 over e, which is what you would get if you didn't have any sampling, if you found the exact centroid, minus, so you get a little bit less, square root of n divided by m times the original volume. N is the dimension, m is the number of sample points. So if I took m to be a large enough constant times the dimension, you're still dropping by a constant factor. So you get the same, right, progress. And in fact, if you work this out, the total number of iterations that this takes to solve the convex optimization problem in full generality is linear in the dimension, unlike the ellipsoid, which takes quadratic. And there was already another algorithm by Vaidya, which also takes linear number of iterations. Okay, that's problem 1. Problem 2 is volume. Now, for volume, the starting point was actually this very interesting lower bound that came up after optimization was known to be solvable in polynomial time. And the lower bound says the following: due to allocation strengthened by Bharani and Furedi, take any deterministic algorithm that uses at most n to the a, where a is a parameter now, doesn't have to be a constant, it's just a parameter, n to the a membership calls to an oracle for a convex body. So it's asking n to the a times, is this point in the set or not? Is this point in the set or not? N to the a times. And then it computes 2 numbers and claims that the volume lies between those 2 numbers. So for any such algorithm, there is some convex body on which the ratio by which it must be off in order to be guaranteed to be correct is Cn over a log n to the n over 2. So if you take a to be any constant, so polynomial number of queries, your approximation factor for the volume is roughly n to the n over 2. In fact, if you want to get an approximation better than constant to the n, you have to use exponentially many queries. So it seems absolutely really hard. There's only one qualification there. This is for any deterministic algorithm. Nevertheless, it was a great surprise when Dyer, Friis, and Kannan came up with a polynomial algorithm to do this, and that's what I'll describe next. So this is the only one of the algorithms I'll discuss that's not from the past decade, as my title indicates. Okay. So you want to estimate the volume to within 1 plus minus epsilon. So what we'll do is break this up into a sequence of, this is a typical, very clever computer science idea. You consider a sequence of balls and their intersections of these balls with the convex body that you care about. The first ball is small enough that it lies completely inside. So its volume you already know, it's a formula. The last ball is large enough that it contains the entire body, so the volume you're computing would be exactly the volume you care about, the volume of the body. And now what you're actually going to do is compute the ratios of successive volumes and multiply these ratios, so volume of the ith to the I plus first to the I plus second, these ratios, and multiply them with the volume of the innermost one. That gives you the volume of the outermost one. This is just a telescopic product. Now, how do you compute these ratios? Well, you have 2 bodies, one inside the other. You want to know what's the ratio of their volumes. Pick random points from the bigger body, see how many fall in the smaller body. That's your estimate. If the ratio you're computing is small, let's say you know it's between 1 and 2, you only need a constant number of samples, or 1 over epsilon squared samples. Now you're going to do this m times, so you need your accuracy to be a little bit better so it doesn't blow up. And so if you're going to do m phases, you need m over epsilon squared samples in each phase. And the m over there is about n times the log of the diameter in order to guarantee that the ratios are factor of 2 at most. And so the total number of samples is n squared. So given that you can sample, you only need n squared samples from different convex bodies, but they're all convex. Okay. And okay, so is this tight? Is this the best we can do? In fact, no. I mean, it is tight in the sense that this is the best setting of parameters here. If you try to make the ratios larger and thereby change the number of samples or the number of phases, this is the optimal setting. N squared is the best you can do if you do this. But if you consider a generalization of this to integration, so let's compute the volume in a slightly different way. Rather than a sequence of convex bodies, let's use a sequence of functions. Okay, and we'll compute their integrals. The functions will all have exactly this form: e to the minus a number ai for the ith function times the length of x. So they're spherically symmetric functions. right? It just depends on, the function value depends only on the distance of x from 0. And the AIs will start out very large, right? So large that most of the mass of the function is contained inside a small ball. Because by the time you go outside this ball, the function is almost 0, so you can just estimate it, the function as the integral over a fixed radius ball, so that's a constant. I mean, that's some parameter you compute offline. And then it's a sequence of integrals that you'll compute, but if you look at the last function in the sequence, we'll choose the parameter small enough, so close to 0, that the function is essentially constant, and therefore its integral is the volume. Now, what does this buy us? The point is that we'll be able to change AI at a rate of 1 minus 1 over root n. So it'll have every root n steps, as opposed to the indicator function algorithm, where you had to go at a rate of 1 over n. You could only increase by 2 to the 1, or 1 plus 1 over n. Here it's 1 minus 1 over root n. And when you do this, so that's the algorithm as I described it, the ratio of integrals, and the number of phases is only square root n because of the rate at which we're changing the parameter. And now you can ask, how many samples do you need to compute each integral? Because after all, the product of everything could be n to the n, and if you're only doing root n phases, one of those integrals that you're computing, one of those ratios that you're computing is exponential in square root n, and therefore you might need exponential square root n samples. But no. In fact, the nature of these functions is such that if I sample from 1 in order to estimate the ratio and use that as the estimate, then of course it has the right expectation, that's how we set it up, but its variance is also bounded. And therefore you only need a constant number of samples in each phase, and the total number of samples across all phases is just linear in n. And this is the best possible for these functions. And now note that this function that we defined is log concave. So it has some very strong convexity properties. We could have used some other function, but we need to be able to sample it still. If you can't sample it, then it's useless. Okay. So this algorithm is something from statistical physics, this type of algorithm, simulated annealing. It's changing. You think of this AI as an inverse temperature, if you're interested. So then that leads us to the question of how to sample. In fact, we've done both optimization and integration by sampling. That was the core of both. So how do you sample? Now, sampling has the simplest algorithm of all, or the most naive algorithm of all. You're just going to walk around randomly for a while, and after a while, output wherever you are. Okay. So here, how do you walk around randomly? So the ball walk is at a point x, you consider a ball of a fixed radius delta, and pick a point randomly in that ball. If the new point is in the set, which is exactly the type of query you can make, then you go there. If it's not, try again. Okay, so you try to take a step. If you stay in the room, you keep going. If you don't, try again. That's one walk. Another one, defined by Bonnet and Smith, was at a point x, you pick a random direction through the current point, so a random line. Consider the chord induced by that line, and on that chord, pick a random point. So you spin around, look in a direction, and then go to a random point in that direction. And you repeat. So whereas in the first walk, you might not take a step once in a while because you were stepping out, here you move every step. This also can be implemented with the type of oracles we're talking about, because you just need to search for the ends of the chord, binary search, another classic computer science tool. So it's not hard to show that for both these and for several other ways to walk around randomly, the distribution of the current point tends to what we want, the uniform distribution in K in this case. But more generally, if we had a log concave density, then we would modulate how we walk, but we would have a density that's proportional to the function that we want to sample from. So the key question is how many steps? Right? So to be efficient, we want the number of steps to be small. So to understand this, we need to define one quantity called the conductance. And what this really is measuring is K is your convex set, or the set, the state space. A is some subset of it, And that probability there stands for each point u, Pu is the measure after when you take one step from u. So you're at u, you take a step, you induce some measure, some distribution. And you're asking, what is the probability that you leave A given that you're at u? And you're adding this up over all u in the set A. So it's just the escape probability of the subset. And the conductance is the conditional escape probability, the probability that you will leave given that you're in the set. Okay. You'll cross over given that you're on one side. What's the probability you go to the other? So for any set. And if this probability is very small, then it follows that you will need a lot of steps. Because you could take a set for which the probability is really small. You will have to take as many steps as it takes for you to cross over, because otherwise you will not be able to reach the right distribution. You at least have to hit the support. So you definitely need this to be large. And a nice upper bound theorem says that, in fact, the rate of convergence is basically inverse quadratic in this parameter. So if you look at, these are two different versions of distance in which you get close to the stationary distribution. But if you want, you can ignore the left-hand sides and just look at the right-hand side. The last parameter, it says 1 minus phi squared over 2 to the t. This phi is the conductance, and t is the number of steps. So every 2 over phi square steps, your distance is getting cut by a constant. Okay? So if phi is large, 2 over phi square is small, and so your mixing is fast. So you would like phi to be efficient, you would like phi to be inverse polynomial, at least inverse polynomial in the dimension. So the proof of these inequalities, by the way, unlike classical Markov chain theory, does not go through what's called the spectral gap for anyone who studied this. It actually is a direct proof relating the conductance to the convergence of the chain by Lovász and Šimanovič. Okay, so how do we bound this conductance? So now we need to bound this escape probability. You're in some subset, you're applying this process, you want to know what's the probability you escape and show that it's large no matter which set you're in, which set you consider. So to think about this, imagine the middle line there denotes the boundary of A. What are the points that have a chance of crossing over? Let's say we're doing the ball walk. There are those points that are near the boundary. This is a high-level description. Those points near the boundary have a chance of crossing over. Those points that are far, I mean, you take a step, you're still inside the set, inside the same set. So in order to show that the escape probability is large, we'll need to show that the points near the boundary take up a large measure of the set. And this becomes a purely geometric property, isoperimetry. What is the boundary of any partition of a convex body? So we'll see that in the next slide. In addition to that, we just need to be able to say that if you're unlikely to cross over, you must be far, pointwise. If 2 points after one step don't overlap in their probability measure, they must already be far apart. I won't go into that, but that is a very geometric argument that depends on the specific walk you're analyzing. Okay. So isoperimetry, now we can forget about why we're doing this, sampling, optimization, integration, just a question about convex sets. I have a convex body and I partition it into 3 sets, arbitrary partition. I'm drawing it as 3 connected sets, but it's really an arbitrary partition, S1, S2, S3. It's really 2 subsets, S1, S2, and they're at some distance, Euclidean distance, ds1, S2. So any pair of points are at a distance at least ds1, S2. One from S1, one from S2, their distance is at least ds1, S2. And you want to know what is the minimum possible measure of S3? Given that these 2 sets are far, is it true that what's left must have large measure? Now, in general, it's not true. You could have a setting where, let's say, you take two balls and bring them close together and they touch. If the 2 sets are almost the entire balls, what's in the middle is very little. Or take a dumbbell-shaped thing, a barbell, and you could have the 2 sets be the 2 ends of the 2 bells, and what's in the middle, they're very far apart, but it's very little measure. But that's not convex. That's highly non-convex. So in the convex setting, in fact, there's a very clean lower bound on the measure. The volume of what's in between is proportional to the smaller of the 2 sides and the distance, and grows inverse is inverse proportional to the diameter of the whole set. And this in terms of these parameters, it's tight. You can achieve equality with just a cylinder. Now this, I stated for volume, this also applies to any log concave density. So I put down a log concave density in space, I partition it, these parts are at some distance. What's the minimum measure of what's in between? Well, it's exactly the same lower bound for any log concave function. Now I want to state my favorite conjecture due to Kannon-Lovász and Šimanovič. It's an isoperimetric conjecture, so it's just it's going to be of the same form. So if there's a stationary distribution, so let's say the uniform distribution of a convex body, and this distribution has some covariance matrix. I'm calling that A. And so, for example, the expected square distance of a point from the centroid, expectation of x1 squared plus x2 squared, the sum of those coordinates deviations from the centroid is exactly the trace of this covariance matrix, because the trace is x1 squared, x2 squared. And that's the sum of the eigenvalues of this matrix. So one way to state this isoperimetric theorem is that the isoperimetric ratio, I'm just abstracting that out as phi f here, is at least some constant divided by the square root of the sum of the eigenvalues of this covariance matrix. And if the body is isotropic, so the covariance matrix is the identity, then this sum is just n, so it's c over square root n. Now you can ask what's the best possible here, and the conjecture is that, in fact, you only need to look at the top eigenvalue. You don't need the sum, you only need the top eigenvalue. And if it were true for isotropic, your isoperimetric ratio, the ratio of the surface or what's in between to the smaller side, would be just a constant, independent of the dimension. Okay, that's the conjecture. I'm happy to discuss further offline. Now, very closely related to this is another conjecture called the thin shell conjecture. So to motivate this, actually, let me skip the motivation. So there is motivation here which tells you why this will help improve the mixing time of random walks and so on. Let's skip that. What does the conjecture say? The conjecture says the following. Assume that you have a convex body in isotropic position, or log concave function in isotropic position. What does that mean? That the expectation of any xi squared is 1, expectation of xi xj is 0. Now, so the expected square distance of a point from the center is n. The expectation of x1 squared is 1 and x2 squared is 1, so their sum is n. So the point itself is about distance square root n. Now you can ask, what is the thickness of an annulus that contains most of the body? So most of the body is in a ball of radius about root n, but really, do you need the whole ball, or is there an annulus in which most of it is contained? And the thin shell conjecture says that in fact the annulus that you need is only a constant, independent of the dimension. So the body is in a ball of radius root n, but really it's just an annulus of thickness 1. And so for example, this thickness is achieved by a Gaussian density. So for a Gaussian density, you have thickness 1, or by the uniform density on a cube, hypercube. The conjecture is that no matter what convex body, what log concave function you have, you still have a constant upper bound. We don't know how to prove it. It turns out that KLS conjecture, the one on the previous page, implies this one and implies another one called the slicing conjecture, which has been talked about a lot over the past 3 decades. Okay, so going back to why we came to these conjectures, given good isoperimetry, we can then conclude that for a convex set, the ball walk, starting from what's called a warm distribution, so you can't start anywhere, and we'll see why in a second. If you start from a point that's somewhat random, then you will reach a random point in polynomial number of steps. Or if you start from a random point, you'll reach another nearly independent random point in a polynomial number of steps. And then there are many questions here. How do you get the first random point? Is this really practical, or is it some polynomial bound? What if the diameter is very large, and so on? I won't address all these issues. They're discussed both in this survey and in another one on geometric random walks. But I do want to make one, say a bit more about one of them, which is how do you get the first one? And so by means of this illustration here, So the cone there represents some corner of a convex body, and if you happen to start your walk somewhere deep in that cone, then the ball walk is stuck on the first step. Every step you take is trying to go out. The volume of the ball that's actually contained inside could be a negligible fraction, and so you're not even moving. And that's why you need a somewhat warm start, a good start somehow. So there are various tricks to do that. Let me not get. What about hit and run? Hit and run we know will move, but is it just going to oscillate in that corner and never leave, or is it actually going to escape? And it turns out it actually escapes at an exponential rate. It just zooms out of any corner. Now, to prove that, the classical setting of isoperimetry, where you take two subsets and look at their minimum distance, is just too coarse. Because you could have this situation where you have a subset S1 and a subset S2, and they're close somewhere and far at other places, but because they're close somewhere, you're not able to get a lower bound on what's in between. So what you'd like is a weighted, an average distance rather than a minimum distance. And this turned out to be a new direction for the field of isoperimetry. And without going into the full details here, what one can do is define the natural notion of distance for the hit and run, which turns out to be this classical cross ratio or Hilbert distance. And then put a weight on every point, which is the minimum distance of the two subsets along lines through that point. So it's minimum for every point, but then you average over all points. So it's an average over all points of the minimum through every point, rather than just the global minimum. And when you do that, that's the isoperimetric inequality you get. And in fact, you can prove that not only that this walk mixes in polynomial time no matter where you start. Start anywhere deep as you like in a corner, and you mix in polynomial time. The conductance, as we defined it, is 1 over n times the diameter for any subset. And this gives an n-cube sampling algorithm. The star hides log factors and factors depending on epsilon. So to conclude the sampling part, there's some questions, lots of interesting questions, I think. One is, does the ball walk actually mix if you start at a nice deep point like the centroid? We don't know the answer. How do you know that you've walked long enough? Is there some way to decide on the fly, or by looking at the points that you've been to so far, that you're actually close to the target distribution? Right now you say, walk for n-cube steps and you'll be close. That's not a satisfactory algorithm. And then the walks we've talked about so far use only a membership oracle. But for convex bodies, we almost always have a separation oracle, where not only are you able to decide that the point is outside, but if it's outside, you have a plane that separates the point from the set. And then could you use this to design faster walks? And there's one process in particular that seems very attractive, called the reflection walk. So let me describe it for the case of when the body is a polytope. You start at some point. Imagine that you're picking a random point on a large ball. The ball might be bigger than the body even. You pick a random point. Now that defines a line. Now you try to go to that point that you define along the line. But as you go, you might hit a boundary. If you hit a boundary, just reflect. Take that line, reflect it, keep going till you reach the point. That's it. Repeat this process. So you picked a random point on a large ball, and to get there, you keep reflecting whenever you hit a boundary. And as far as we know, the complexity of this process could be linear in the dimension. But we don't know an upper bound. Okay. Rounding, we've discussed this several times, and the diameter has been coming into the picture. The point about rounding, one implication is that when you round, the diameter becomes small, and you don't have to worry about exponentially large diameters and so on. So all we need to do to round is compute the transformation that puts the body in isotropic position or near isotropic position. Well, how do you do that? Well, remember, what is isotropic position? All you need is to take the covariance matrix and make it the identity. So you just need to estimate the covariance matrix. How do you estimate the covariance matrix? Take a sample. Take a random sample, take the covariance of the sample. That should approximate the covariance of the full distribution. So it's not hard to show that n squared samples suffice. Turns out that you only need linear in n random points for any log concave function. So you take, and the epsilon is if you want to approximate the isotropic position, the transformation to within 1 plus minus epsilon. Okay, so if you wanted to approximate to within a constant, say 2 there, ignore the C epsilon, you just need order n points, take order n random points from the body, compute a transformation that puts the sample in isotropic position, apply that transformation to the original body, and you're 2 isotropic. So that's what happens with. So again, there's really only one algorithm we talked about so far, and that's sampling these functions, and everything else is built on that. I thought about drawing a picture, but then the picture basically looks like a star, so I didn't draw it. So just to summarize here are some of the improvements of what's happened, and the volume problem has been a vehicle for all these things. Dyer, Friis, and Curran, and this second column is a quantitative illustration of progress, one view of progress, the exponent of the volume algorithm. So it started at 23, and then everything was new at that point. 16, localization, that's a technique for proving these isoperimetric inequalities. 10, where they extended to integration. 10, the ball walk was introduced. The original walk by Dyer, Friis, and Curran was a walk on a discrete subset of space on a fine integer, on a fine lattice. 8 was just improved error analysis. Lovász, Šimanovič had multiple improvements. They introduced more general techniques, this mixing directly from conductance and things like that. KLS, they introduced isotropy and an analysis technique called the speedy walk. And then with Lovász, the annealing algorithm and this notion of weighted isoperimetry. And then this all extends to integration. You can integrate any log concave function in n to the 4 steps, or maximize. Okay, the last problem, learning. So given access, so what's the learning problem in general? You're given access to random points from an unknown distribution, possibly unknown. In some cases, you assume it's known, and still very interesting question. Say, labeled by an unknown function. The function is definitely unknown, possibly from a class of functions that you know about. Always from some class of functions. And the goal is to find an efficient rule that correctly labels most of the distribution, so that given a new point from the same distribution, you can label it correctly most of the time. So the input, so the parameters, there's a distribution in Rn, there's a labeling function, -1, 1, or 0, 1, and then there is error parameters. Epsilon is telling you that you must correctly classify 1 minus epsilon of the distribution. Delta is just the failure probability of the algorithm. That in all the cases we'll consider, we can control as log 1 over delta, so I'm going to ignore that from now on. That's the probability of correctness of the algorithm itself, not the rule. Okay, so learning is really, you can think of the concept that you're learning as an indicator function, right? The part where it's 1 and the part where it's 0. So for what sets do we expect the learning problem to be easy or polynomially solvable? Right, so if you're efficiently learnable, in some sense, this set is easy. What are some candidate easy sets? So you might imagine maybe low dimensional sets. The set is inherently low dimensional, and then you have noisy features, or maybe convex sets, right? That's what's worked so far. Okay, so unfortunately, learning convex sets is not easy in general. This is resolved by Clivens, O'Donnell, and Servideo, where the input distribution is a Gaussian, standard Gaussian. There's a convex body sitting there, unknown to you, of n to the root n, but that's so it's not polynomial. And then resolved by Naveen Goyal and Luis Rademacher, closely related but different, is suppose there were no labels, you just get random points from the uniform distribution of a convex body. Or you just get random points. You already have a random oracle. How many points do you need to correctly learn the set, in the sense that given new points, you can decide whether they're in the set or not. You don't really need labels if all the points you're given are random from the set. And again, the lower bound is 2 to the root n. Same function, but it's a very different, it's a different construction. I don't want to say very different. And maybe most surprising in this line is a result by Eldan from earlier this year. It says, okay, in those two cases, the goal was to learn the function given random points. learn the set. What if all you cared about was computing the volume given random points? Okay? Still, there exists at epsilon, the epsilon he proves is like 0.1, so that you need 2 to the n to the 0.1 random points before you can estimate the volume. There's no contradiction with the polynomial upper bounds, because those assume that you have a membership oracle, so you can sample random points from any subset of the original convex set, or any variant of it. Here, you're just given random points, one shot from the body. You don't have any other access to the body. How many do you need? And that, even to estimate the volume, you need exponential. Now, why is this so hard? Well, the sets that lead to these lower bounds are all very similar in the following sense. They're all polytopes, but they're all polytopes with an exponential number of facets. The number of facets is something like 2 to the root n. Okay. So if you define, and they're random in the first and the third case, if you're defining a random polytope with so many facets, how do you expect somebody to come up with a polynomial description of it? In fact, maybe there's no other description. That's what they're saying, no other description other than the facets themselves, essentially. But the volume, I mean, maybe the volume should be, even that is hard. Okay, so since you have so many facets and that's what you're trying to learn, okay, it's hard. What about, so that's what I was saying. What about if the body has some succinct representation? So, for example, let's say it's an m-facet polytope. It's a polytope with m facets. I don't know what it is, but it's m-facet polytope, or at most m facets. Can you learn it then? I think this is one of the most interesting, possibly solvable open problems out there today. And it's an m-facet polytope. Can you learn it in polynomial time? The sample complexity is no longer an issue. If it's m-facet polytope, you only need order mn samples to do everything. So it's a time complex. It's an algorithmic question here. And this captures lots of other problems, such as learning DNF and so on. Okay. What can we do? So this is a question that I'd like to understand, but I don't. Okay. So let's make it even simpler. We'll stay convex, but the number of half spaces defining the set is k. Okay, where k might be smaller than the dimension even. So it's just k half spaces. What's the complexity of learning this? So k equal to 1, we know how to do very well. K equal to 1 is one half space, right? And that's linear programming. You just have to find a half space that contains a given set of points if there exists one, and there will exist one in the learning problem. So it's equivalent to linear programming, convex problem. K equal to 2, open. We don't know anything how to do it in general D, no real hardness result to speak of. I mean, learning hardness results are hard to come by because you can learn it using something else. You just have to come up with a polynomial rule. However, for some special distributions, so if the distribution is centrally symmetric or log concave, for k equal to 2, there are polynomial algorithms. Now, I think of these as low dimensional because all you need to describe the labeling function is the, in the k equal to 1 case, you just need the normal vector. So you project to that vector, you know whether you're, in the half space, you just need the normal vector, then you know whether you're above the threshold or below the threshold. Same thing for the 2 case, you just need to know the projections to the subspace spanned by those 2 normal vectors. So it's really a 2-dimensional labeling function. Okay. Now if you go to k instead of 2, then for some special distributions there are some results. So if it's uniform in a ball, then Blum and Kannan, Avram Blum and Ravi Kannan, give an algorithm that's polynomial for any fixed k, doubly exponential. And I had an algorithm for log concave distributions, so originally for nearly uniform and recently extended to log concave, which grows as a single exponential in k. And these guys, Clivens, O'Donnell, and Silverio, in the same paper where they proved the lower bound, for the Gaussian case, had an upper bound of n to the order log k over epsilon to the 4. So a much better dependence on k, worse on epsilon. That algorithm is also agnostic for those who do learning theory. Still, if you want to get a polynomial algorithm, you have to assume k is a constant. So can we really learn for more than a constant number of half spaces in polynomial time for any nice distribution even? And the answer is yes, as of this here. So let the distribution be any Gaussian. The intersection of k half spaces can be learned in time that's polynomial in all parameters plus linear in n times a function of k alone. Not n. There's no dependence on n there. Okay? And the function is not terrible. It's just the minimum of the two earlier functions. We're just taking the dimension to be k. Okay? So in particular, it's poly n for k all the way up to 2 to the square root log n. I don't know if you've heard of this conference called SLOGN. It's being considered as an alternative to ICS, the Innovations Conference. So SLOGN, the emphasis is that any paper submitted should have a square root log n in it. So I did not submit it there, but anyway. Okay, so how does this work? And I think in the remaining minus 2 minutes, I'll try to describe one last idea. Feel free to not listen. So the normal subspace is the span of the normals to these planes. Okay, so the span of these k normals. And as you can see, the labeling function, the set that's 1, say, is completely defined by this subspace, and then orthogonal to it, it's just a lifting. Because the other subplane, the other coordinates are irrelevant. All the, you project to this plane, that defines your set, and then everything else is irrelevant. So it looks like a cylinder in the rest of the dimensions. And in fact, you don't need to be k normals, you just need your set to have normal subspace of dimension k for this thing to work. And the reason I want to say this is because the algorithm is different now, and it's this classical PCA. So here's the algorithm. Make the sample, the full sample of positive and negative points isotropic. It's just an affine transformation. Then look at only the positive points, shift to center their mean at 0, and find the smallest k singular vectors. So the k singular vectors that have the smallest singular values, and project to their span. So now you have a k-dimensional problem, and the claim is this span of the smallest k singular values is in fact very close to the true relevant subspace. Okay, and I will actually try to indicate why that's the case. So this is just stating what I just said, that there's a labeling function so that you can figure out this subspace by applying that algorithm. In the case of k half spaces, you only need a polynomial number of samples, and for general convex sets with normal subspace of dimension k, you need exponential in k, polynomial in n. So why is this? And there's this nice property that Gaussian space has. So after you enforce isotropy, the variance is 1 in every direction. And in fact, if you look at the positive examples, orthogonal to the normal subspace, you just have a Gaussian at every point, so the variance is still 1. What about in the normal subspace? So orthogonal to the normal subspace, it was 1, whether you restrict to one point or any subset, it's still 1, because every point orthogonal to it is just a Gaussian, standard Gaussian. Now, what about in the normal subspace? And the main lemma, which I won't go through, is that in the normal subspace, the variance can only go down. It cannot go up. If you make a convex, if you take Gaussian distribution, any Gaussian, if you take Gaussian distribution and restrict to a convex subset, convex set, the variances in any direction can only go down. And that's why the smallest k singular vectors capture your subspace. Okay, now you have to worry about sampling errors and so on, but that's standard technical difficulties. So the case b equals infinity, so we need a quantitative decrease. Without the quantitative decrease, this lemma was essentially known. It's the Braskamp-Leib inequality. With the decrease, which we, that's what's new. And in fact, it verifies the KLS hyperplane conjecture for the case when the distribution is Gaussian. But that's a very special case. Now, last slide, or almost. I want to mention that this monotonicity, the variance going down when you make a convex restriction, is unexpected. It seems like, oh yeah, you go take a smaller subset, variance should go down. No. Suppose you had the uniform distribution on a ball instead of the Gaussian. Just uniform on a ball. It looks close to a Gaussian. Okay. Now I restrict to a cylinder, a narrow bar inside it. The variance in the direction of the axis of the cylinder actually is much higher for this bar than it is for the whole ball. For the whole ball, the variance is only about the radius squared divided by n, whereas for this bar, it's radius squared. So the fact that it goes down in every direction for Gaussian space is not something you would expect. Okay, so this is the last slide. What can we do beyond convexity? So I mentioned star-shaped sets. Turns out you can sample these star-shaped sets efficiently. So the sampling problem is easy, and therefore you can compute the volume, but linear optimization is hard. Hard even to do approximately. So you can write Max Clique as a star-shaped minimization problem. Question, manifolds. Like, we would like to extend these things from convex sets to, manifolds are one possible extension, surfaces with some properties. How about discrete subsets of convex sets? All lattice points inside a convex body. Can we try to count them or sample them or maximize over them? And we only know things about very special cases. And then finally, what I call the problem of learning subspace juntas. Juntas are functions of a small number of variables out of many variables. Subspace juntas are unknown function that depends only on a k-dimensional subspace rather than k original coordinates. So for example, the intersection of k half spaces is a k subspace junta. And it turns out, while we don't understand the problem in general, it turns out that it's possible to solve this problem when the distribution on the irrelevant subspace is independent of the distribution of the relevant subspace. And the algorithm is an extension of PCA to higher moments. You actually need to find local optima of higher moments. PCA is second moment, you need to do higher moments. Okay, I'll stop here. Thanks for the extra time and for listening to me.
Maybe we have questions? Yes.
What happens in high complexity? Maybe the complexity has there.
Right. So for all but the learning problem, the bounds that I gave are actually on the time complexity. Yeah. In the learning setting, for the last thing that I described, where you have functions, an intersection of k half spaces under a Gaussian distribution, that was time complexity as well. For general polytopes, sample complexity we know, but time complexity is wide open. This last result I'm mentioning is also time complexity. So I tried to mention the theorems where we also had some efficient algorithms, not just sample complexity bounds.
Other questions? Yes.
If you say that somehow the bad examples in the learning setting are derived from polytopes which have many facets, phases, I mean somehow this polytope would have high descriptional complexity.
That's right.
Is it possible, not just by the way you described just in a general setting, say Kolmogorov complexity or whatever, to limit this sort of description complexity of this object in order to obtain object results?
Yeah, that's a good question. Is there a complexity measure under which we could say, can you learn convex bodies that have small, for example, Kolmogorov complexity? So I don't know. The one that we have some progress on is when you explicitly limit the number of half spaces. But any other description, an abstract version of that would be when you have an efficient separation oracle. Not only that it exists, but it's actually polynomial time computable, say. So that's a lot of structure, but I don't know what exactly that implies.
One question? Yes.
For some of the learning algorithms learn for arbitrary distribution intersection of half spaces, but with margin. When the distribution is such that the separating hyperplanes are far.
Yes.
So can we sort of assume some sort of margin condition for the good distributions and then get something better?
Right. So certainly there's been work with margins, so robust concepts for the intersection of half spaces problem, for example. But again, I'm not aware of something which gives a polynomial algorithm, let's say if you have m facets. Yeah. So there are better bounds for the settings in which you have a bounded number of half spaces. So for example, for 2 half spaces, if you have a margin, you can learn. But and then for more general distributions than we described. Exactly, you can do for more general, but still bounded number of half spaces.
So what about for good distributions and
It's a good question. For good distributions, so for example, can you learn polytopes that are robust? Let's say then, I don't know. I mean, I don't know of an algorithm, but yeah.
Yeah, maybe a last question? Or maybe not then. Maybe we'll meet again and talk about